We'll take a deep dive into backpropagation and look at how it works. We'll break apart a function into components and then take the derivative of each component separately, then combine those components to find the derivative of the whole function. We'll then use our knowledge to build a miniature PyTorch that can automatically differentiate functions. At this point, we've built quite a few different neural network architectures. We've done a forward pass, calculated the loss, and then done the backward pass. And what we've essentially done, although we haven't done it explicitly, is construct what's called a computational graph. And a computational graph looks like this. It breaks a function apart into pieces, and each piece is called a node. It's where you see the oval in this diagram. And the arrows between the ovals are called edges. They show how one piece connects to another piece. This diagram might not make sense now, but this is the computational graph for the Softmax function. And we used the Softmax function in an earlier lesson on classification. So what's the point of the computational graph? Basically, by reversing the computational graph, we can run backpropagation. So in the forward pass, all these arrows go in one direction. In the backward pass, they go in the opposite direction. And what that lets us do, if we understand the computational graph, is really understand how gradients flow through our network, which will help us tune and scale neural networks more effectively. So today, what we're really going to learn about is how gradients flow in the backward pass through the computational graph. We'll take a very detailed look at that. And initially, we're going to use the Softmax function as our example. So as a refresher, this is the Softmax function. So this weird squiggly line is Softmax. And you basically take an input array, you raise each item in the input array, you raise e to the power of each item in the input array, and then you divide by the sum. And the Softmax function will give you outputs between 0 and 1, and all of the outputs will add to 1. So it can be interpreted as probabilities, which it is in classification models. So here's how the function looks in code. This is using NumPy. So this first line will raise all of our e to the power of all of our values. Then we will divide by the sum, and then we'll return our output. Let's run an example through this function just so you can build some intuition for what it does. So we'll define some x and y values, just fake values. X is going to be a matrix with 5 rows and 3 columns, corresponding to the output of the last layer of a neural network. So we have 3 targets we're trying to predict, and this is giving us the output of the network for each of those targets for 5 different rows, so 5 different training examples. Then we can create our actual targets. These will just be fake values. So we're using NumPy zeros like to basically create a matrix with the same shape as X, but with zeros everywhere. And then we're randomly going to define what the target column should be in each column. So this is a little bit convoluted, but all it's doing is in each row, it's picking a column that it's going to return the index of. And then what we'll do is we'll just say y ins equals 1. And this will just give us a random target for each row of our predictors. So we'll take a look at X. We have 5 rows and 3 columns. We take a look at Y. It is mostly zeros, but a 1 corresponds to the quote unquote correct target. And we can use this to test our Softmax function. All right, now it's very common when you're doing a Softmax in the real world to subtract the maximum value of your inputs in order to create numerical stability. If you don't, you sometimes end up raising e to a very high power, which can overflow your data container, your data type. So we'll just normalize our x values by saying x equals x minus numpy.max x, axis equals -1. So we're finding the maximum of each row, and then we're going to reshape this to just have a single column. All right, so that's how this ends up looking. We've subtracted the max from each row. So the maximum value is 0, and the other values are less than 0. And then we can actually run our Softmax function on our normalized data. We'll see how that looks. All right, so you can see we end up here with essentially what look like probabilities. Each row adds to 1, and it's essentially giving us the chance that the prediction is actually that column. So this is basically saying there's a 44% chance that this is the actual class that we're trying to output, 29% chance here, etc. Okay, and to get a little bit more intuition about why we subtract the max, let's take a quick look at a common NumPy data type, the float 16, and we'll look at the maximum value that can be represented in float 16. So this is the maximum value that we can store in float 16. So if we go above this value, we'll actually end up getting an error. So let's take a look at what this does. 6.55 E50. So you can see that this value has actually overflowed and is now showing as infinity. That's because the value is actually too large to store in float 16. So this is a little bit of an aside. If you do train neural networks, you'll actually run into this a lot, which is why I'm covering it. But it's why we subtract the max from the softmax. Okay, so now we understand the softmax function. Now we can actually break it into pieces and actually build what I'm going to call a staged softmax, where we calculate each value in stages. So this will look something like this. Stick it in a diagram. So we have our input x, then exp, we raise e to the power x, and then we pass that exp into the sum, where we compute the sum of all of the values, and then we pass it into the divide, where we divide each value by the sum. And then we have our softmax output. I'm leaving the subtracting the max out of this just to make it simpler. But in a real-world implementation, you would subtract the max as part of this too. All right, and then these are the 3 operations that we're doing. So in a computational graph, you have basic operations that you put together to construct something more complex. So these are our 3 basic operations here. And what this lets us do in backpropagation is essentially compute the derivative of each piece separately and then multiply them together by the chain rule, which we've covered in earlier lessons, to get the final derivative. It also makes the forward pass a little bit easier to understand. So don't worry, I'll show you how the chain rule works, and I'll show you how the backward and forward pass works in stages. Okay. So to make this a little bit simpler to compute, instead of division, we're actually going to use multiplication. And if you'll remember, 5 divided by 4 is the same as 5 times 1 divided by 4. And 1 divided by 4 is actually the same as 4 to the power negative 1. This. So what we can do here is actually turn our divide into a power operation where we raise a value to the power negative 1 combined with a multiply. So we'll actually end up with these 4 operations. It's a little bit easier to take the derivative of a multiplication and a power than a division, which is why we convert the division into 2 steps. Okay, so now we can build our staged softmax. So the first thing we'll do is we raise e to the power x. Then we'll sum all of our raised values. So this is step 2. Then we'll do step 3, which is our power step, where we raise to the power negative 1. So summed goes to the power negative 1. And finally, we just multiply the 2 together. And that gives us our staged softmax, which we can visually just look through and confirm is the same as our earlier softmax function. It gives the same output. It's just breaking it up into discrete steps, individual operations. Okay, we can now take the derivative of these individual operations. So let's take a look at the steps and how they look in a backward pass. All right, so we start with our derivative of the loss, which in this case, we would take the output of softmax, calculate the loss, and then feed it back in to do the backward pass of the network. Then we do the backward pass through our multiplication node, And that feeds data back into two places: the power node, where we raised our input value to the power -1, and our original e to the value node. Because remember, the multiplication is multiplying the sum, 1 over the sum, times e to the power. So it's actually getting input data from two different nodes. So we pass the gradient back to two different places. So this shows you how the gradient flows. And by the chain rule, to get the derivative of the loss with respect to a node, we just find the derivatives with respect to the previous nodes and multiply them together. So here are the rough steps that we'll need to follow to reverse our stage softmax and compute the gradient with respect to the input, with respect to x. So we start at the last step, we take in the loss gradient, and we multiply by the derivative of the final step. Then we pass the gradient to the previous operation, and then we continue calculating the derivative of each operation and multiplying. Then we continue until we get to the x node. All right, so the first thing we need to do in order to do this backward pass is calculate our loss. So just like we did in our classification lesson earlier, we're going to use negative log likelihood, which is just the sum of all of the potential outputs times our prediction. So we're just taking each row of y and multiplying it by each row of our predictions. And as you may know, y is one hot encoded here. Only one target is correct. So most positions in y are 0. Only one position is 1. Which means that really this simplifies to just find I, the position where y equals 1, and then multiply by the log probability at that position. So you're essentially multiplying the correct target, which is 1, by the probability that the network assigned to that target. All right, so we can solve this by breaking it down into steps. So first we have our log. The derivative of a natural log with base e is 1 over the input. And then the derivative with respect to p is negative y. Since we're multiplying negative y by log p, it's scaled proportionally to y. And I talked about this in an earlier lesson on gradient descent, so I'm not going to cover these two specific derivatives too much. But by the chain rule, if we multiply these two together, we get the derivative of the entire function, which is this. So it's just negative y divided by the probability. And that's the derivative of our loss with respect to the probability that we assigned to each output class. So basically what this is saying is if we increase the probability, the loss should decrease, and if we decrease the probability, the loss should increase, which is what this is doing. And if you're not sure what's going on, in the classification lesson, we took a deeper look at this and how the actual gradient looks. But the function, if we just write it out, is pretty simple. The derivative of negative log likelihood is just -1 times our y value divided by our prediction. So then we can compute our gradient of loss with respect to p, our probabilities output from our quote-unquote network, our fake data here. So this is our loss gradient. And you'll notice it's 0 everywhere y is 0, and it has a value in other places. The closer this value is to 0, the higher probability we assign that that was the correct class. Okay, now we can calculate the softmax derivative by reversing what we did in the forward pass. All right, so these are the derivatives of each specific node in our computational graph. And this is much, much easier than computing the derivative of the whole softmax function all at once. It's much simpler to break it up into pieces and compute the derivative of each piece, since derivatives of very, very small functions like e to the x are much easier to compute than derivatives of a much more complex function. Okay, so very, very cool, but the derivative of e to the x is e to the x, so we can just use the same value as our derivative. Now, our sum will combine all of the input operations into one. So any change to any input coming into the sum will affect the sum proportionally. So we actually distribute the gradient over all of the input elements. For a power, the derivative of x to the -1 is -1 times x to the -2. And that's true for any power. The derivative of x squared is 2 times x to the 1. And if we multiply two items, the derivative with respect to x is y, and the derivative with respect to y is x, because we're proportionally multiplying one value by the other. So if we add 1 to x, we'll actually increase the output by y, since we're multiplying y by x plus 1. So the derivative is essentially the rate of change of the function if we change an input to the function. So how does the output of this function change if you change the input? And that's what these derivatives tell us. Okay, so now we can calculate our backward pass, or our derivatives. So we'll start with the final item in our computational graph. So that is loss grad times POW. Okay, and to understand what this is and what's happening, let's actually pull down some of the code from earlier. All right, so let's just copy paste this. Okay, so this is our forward pass of our stage softmax. So you remember raised was when we raised e to the power x. So raised grad is the grad against the outputs of raised. And the last step in our stage softmax was when we multiplied raised, which is e to the power x, times our power, which was the sum to the power -1. So the grad against raised is the loss grad times POW. Since if we increase raised, we scale our output by POW, since we're multiplying raised by POW in the last step. Power. So I hope that makes sense. If it doesn't make sense, just really write the code and think about it. Remember, the derivative of a multiplication with respect to one term is the other term, since that term is being scaled by the other term. You can also look at this diagram up here. So essentially what we just calculated is the gradient with respect to the output of the EXP node, which is just the gradient of the loss times the forward pass output of the POW node. Okay, and then we'll do the same thing. We'll calculate the gradient with respect to the output of the POW node, which is just the loss grad times the input from raised, because again, the multiply. Then what we need to do is reshape our loss gradient to match the output size of POW. So in the forward pass, POW only had one column because it came after the sum. But loss grad has 3 columns. But we need to find the gradient with respect to the input to this node. So the output of POW was the input to this last multiplication node. So to find the gradient with respect to the output of the POW node, we actually need to do a sum operation. So that's what we're going to do. We're just going to sum that gradient across to match the shape of POW in the forward pass. Okay, then we're going to take our POW grad, and we're going to calculate the gradient with respect to our sum node in our forward pass. So this will just be summed gradient. So sum gradient equals -1 times sum to the power -2, because we just talked about the derivative of a power, times POW grad. So we're essentially taking the gradient input, we're taking the gradient from POW, and then we're multiplying it by the derivative of summed. Then what we're going to do is we're going to find the second gradient against this EXP node. So this EXP node is going to receive 2 gradients from 2 different nodes. So we already calculated the gradient it receives from the multiplication node. Now we need to calculate the gradient it receives from the sum node. Okay, so we're going to say raised grad 2 is just numpy.ones like raised times summed grad. And this is because summed actually adds up all of the values in the forward pass, right? The sum operation added up everything that came out of this node. So we're just distributing the gradient evenly across all of those input values that came out of the exp node. And we talked a little bit about the definition of the derivative of a sum, and that's right here. This is why we do that. Okay, now we just add the two gradients coming into that exp node together, and then we have our final stage softmax gradient, which is just passing that gradient across the exp node, which is multiplying by the derivative of the exp node, which is just e to the power x. Okay, so we've broken the softmax apart into stages. This is not a lot of code, but it is a lot of complex concepts. So let me just go through this one more time, and if you still don't get it, read the explanation, look at the diagrams, write code. It really takes multiple tries to get this. It's not a simple concept. Okay, so we first have our loss gradient, which is the gradient with respect to the output of this multiplication node in the forward pass. All right, so then what we want to do is convert this to a gradient against the output of POW and a gradient against the output of EXP. And to do that, we pass it across this node and multiply by the derivative of this node. So we first take our loss gradient and multiply it by POW. And POW is the derivative of the multiplication with respect to the output of this EXP node. And we do it with, on the other side too, we multiply the gradient by the output of the EXP node, and that gives us the gradient with respect to the POW node. So that's what we're doing here. Then we need to add together all of the values in that POW grad, because the shape of the output data of the POW node only has one column, whereas the loss grad has 3 columns. So we just need to reverse that sum operation that we did in this node. All right, then we find the gradient with respect to the sum node, which is the gradient with respect to the POW node times the derivative of the POW node, which is just -1 times the output of the sum node to the power 2. Because in the forward pass, we raise summed to the power -1, and the derivative of that is -1 times sum to the power -2. Okay, then we take the summed gradient and find the derivative of that, which is just distributing the gradient across the inputs, which is the output of, so the output of this EXP node in the forward pass went into the sum node. And so the derivative of the sum node is just distributing the gradient across the shape of the input data, which had 3 columns. Okay, then we add together the incoming gradients to the EXP node, and then we multiply by the derivative of the EXP node, which is just e to the power x again. All right, so this gives us our staged softmax gradient. All right, so let's take a look at stage softmax grad. And we'll need to compare this to just a correct gradient. So the derivative of softmax, if you have done it the analytic way, is this. So it's basically the softmax of I, which is the correct index, multiplied by I equals j, which equals 1 if I index equals the j index and 0 otherwise, minus softmax of j. So for example, let's say you were taking the softmax of this list right here, 0.28, 0.25, 0.47. So we would compare each element to each other element. So we would start at element 0, which is 0.28, and then we would compare it to itself. And then I would be 0 and j would be 0. So 0.28, 0, 0. Then we move on. At this point, the equation would be 0.28 times 1 minus 0.28. All right, then we move on to 0, 1. And then at this point, the equation would be 0.28 times 0 minus 0.25, right? Because this is called the Kronecker delta. I didn't write it out as the Kronecker delta because it's a little crazy math symbol. But this basically checks if they're equal and is a 1 if they're equal and a 0 otherwise. All right, so we keep doing this until we construct a matrix. And the matrix looks something like this. So why do we do this? Why do we have to compare every value against every other value in the same row? The reason why we need to do that is because changing any one of these values will actually change the softmax of every value, right? Because the softmax has a sum term in it. So you add all of the values together. So if we changed any single term, like if we change this to 0.27, the softmax of everything would change. So that's why we need to actually do this complicated matrix in order to calculate the derivative. So we can write a function to calculate the derivative, which will look like this. We first initialize output, which is just going to be a placeholder array that will eventually store the softmax output. Then we loop through each row in our input softmax. We extract a single row. We essentially do this calculation, this si I equals j minus sj for each row. Then we calculate the gradient against that single row. If you're not familiar with how this works, I'm not going to go into too much detail, but you can experiment on your own. And then what we do is we find the gradient of this single row, and then we add it into our output. So the output by the end will give us the gradient with respect to our softmax. So we pass softmax and a loss gradient in, and we get the derivative out. Okay, so we can calculate our derived softmax gradient, and then we can check if this is similar to the output from our stage softmax. And to do that, we can use the numpy all close function. Sometimes when you're doing computations in NumPy, you can get slightly different results, even though the underlying numbers should be the same. So that's why we use all close. Stage softmax grad. So we'll just check if these are actually equal, and they are. So this means that our staged softmax, where we split the softmax into pieces, is equal to just taking the derivative of the entire softmax function all at once. And trust me, this staged is complex for sure, but it's a lot easier than finding the derivative of the softmax function. Well, if you know calculus really well, maybe not. But if you don't, it's way easier to split it up into pieces. Okay, so what have we done? We have constructed a forward computational graph. We have done backpropagation against that graph, and we've proved that our backpropagation was equal to what we'd get from just taking the derivative of the whole function, which is what all this was. Okay, we can also double check and make sure that our gradient is equal to the output of the loss function combined with softmax. So you may remember from the classification lesson that one of the reasons why we use negative log likelihood with softmax is the derivative of NLL. So the derivative of NLL softmax x. So let's say this equals p, and our target is y. Sorry. So the derivative of this would just be softmax x minus y of this whole thing together. So we can also just double check that this is true in our code. So we take our stage softmax gradient, and then we subtract y from our stage softmax, and we've confirmed that yes, this is correct. So we know that the way that we did our backward pass is correct. You might be wondering why we made it so complicated when we could have just done this. It was really to build intuition around how this backward pass works. It's really, really important when you're training neural networks to understand how gradients flow through the system. And we'll use our knowledge that we just built to actually create a miniature PyTorch. So it will basically do the forward pass and then automatically do the backward pass for us. So this will help us understand how PyTorch AutoGrad works. Okay, so you might remember this computational graph from much earlier. Basically, what we're going to do is create this computational graph, but we're going to use a separate class for each node. And that class is basically going to know how to reverse itself, so that when we pass data through, it will automatically know how to reverse itself and do the backward pass. So I've already written a class called node, which is essentially a node in this graph, and it has some nice methods that will help us out. So apply forward will just run the forward pass up until the node it's called on. Apply backward will run the backward pass. Zero grad will zero out the gradient before a backward pass, and I'll talk a little bit about that. And then we have generate graph, which will help us visualize, and generate derivative chains, which will help us see, applying the chain rule, the chain of partial derivatives leading up to a point. So what we're going to do is subclass the node class and implement the forward and backward methods using what we've learned about derivatives of different operations. And then we're going to use this to automatically do the backward pass. Okay, so I'm going to just import a few pieces of code I've already written. You can definitely take a look at this code if you want. It's not super important for understanding this lesson and specifically the backward pass, which is why I didn't include it in the lesson, but feel free to read it. So these are just the imports. Then we can define an EXP node. So in the forward pass, the EXP node will take in a array X, and all it'll do is raise e to the power x. All right, then we can write a backward pass, and in the backward pass, it's going to take in a gradient. So the gradient coming in from the node that it's connected to. And all we have to do is pull our x value out of the cache. I automatically have some code that caches the x value. Because if you remember when we did our stage softmax, we often needed the values from the forward pass. So that's what the cache is doing. It's just saving the values from the forward pass. And then all we have to do here is return e to the x times the gradient. This is the exact same thing we did when we split this apart into pieces, right? We took the derivative of each node and multiplied it by the incoming gradient to that node to get the incoming gradient for the previous node. So that's all that's happening here. So this is our EXP node. Then we can write a sum node. And in the forward pass, sum will take in self and x, and it's going to return numpy.sum x axis equals -1. And then we'll reshape that to -1, 1. All right, so this is going to take the sum across each row. And then what it's going to do is it will reshape that to have a single column and as many rows as the input data. The axis argument in NumPy always gets me. All right, then we'll write a backward function. So we'll take in a gradient here. So we'll again pull our x value out of our cache, and then we'll return numpy.ones like x. So this is creating a new array filled with ones with the same shape as x, and we'll multiply it by our gradient, which will essentially copy the gradient into each column in our x data. Okay, then we'll define a POW node for power. And in the forward, this is actually going to take in two values, x and an exponent that we want to raise x to the power of. And we're going to return x times exponent. And we'll have a backward as well, where we take in our gradient. And here we'll do x exponent equals self.cache. So we have two values in our cache now. And then we'll return grad times exponent times x caret caret, or star star, exponent -1, which is the derivative of x to a power. And we'll also return 1. This is just a placeholder value, but we took in two inputs. So for every input that a node takes in, it returns a gradient. So we're returning two gradients. But in this case, exponent's a constant, so the gradient we return does not matter. Okay, then we have a multiply node. And we'll write a quick forward pass here, self xy. we'll return x times y, and then we'll have a backward pass. xy is going to equal self.cache, and we'll return grad times y, grad times x. So the order of these inputs matters, right? So our inputs are x and y. So this is the derivative with respect to x. This is the derivative with respect to y. So those are our nodes. This is basically just taking everything that we've done before and putting all that knowledge together into forward and backward. And it really organizes things nicely in a class, makes it easier to tell what's happening in the forward and backward passes. Okay, then we're going to use a special node that I've created called a parameter node to wrap our input data. And I'll give these a nice description. And I will say needs grad equals true if we want a final gradient to be applied to that node. So there's some nodes, and I'll show you in just a second, that we don't actually want a gradient against. So take a look at that. Okay, so that's our x data, that's our input. And then we're going to raise x to the e to the power x. Okay, e to the power x. This desk field and this out field are just for when we render the graph. So you don't need to worry too much. They don't do anything, they're just labels. So that's all you need to know about those. Okay, then we can sum our raised values, and our out is just going to be sum of e to the x. All right, now we just need a parameter called -1. Desk equals -1. And needs grad equals false. In this case, this is just a constant. We don't actually need a gradient against it. Okay, now we need to invert our sum. So we'll do POW summed -1 out equals 1 divided by sum e to the x. All right, and then we finally do our softmax through multiplication. So we multiply raised and inverted. And our out equals softmax x. All right, so this is the exact same thing we did in the forward pass earlier. We've just wrapped everything in classes. And this will automate the backward pass, which I'll show you in just a second. Okay, so let's go ahead and run this. I did not run this cell first, so I'll go ahead and run that. Inverted. Right. Important to type out your suffixes, huh? Okay, so what this has done in the background is created a computational graph. So we've passed each node to the subsequent nodes. So for example, with summed, we're passed in our EXP node. So the computer in the background knows how the nodes are connected. So we're actually able to generate a graph of this. So this will show the same graph that we saw earlier, but it's actually generated from our code. If we changed our code, this would actually look different, which is very cool. And then we can actually apply the forward pass of our softmax, and I'll store it in a variable called operation softmax. And what we can do is, again, verify that this worked correctly. So we can look at our stage softmax from earlier and our operation softmax and verify that they are equivalent, which is true. Okay, so in this case, our network, we basically defined a bunch of nodes, connected them together, and in the background, our nodes figured out how to pass data between each one and calculate the softmax. That's what this apply forward function does. It traverses the graph to calculate the forward pass. If you're interested in graph traversal, feel free to look at the implementation. It's not a great implementation, so feel free to submit a pull request if you want to make it better. We can also generate a graph in backward mode. So we can take a look at how the backward pass of this graph would work. So you can see we took the multiply node from the right and moved it to the left, and all of the connections are reversed and they're now in red. But you can see how the gradient is going to flow through the network backwards. So from our multiply node, we pass the derivative to the power node and so on. Okay, we now can zero out our gradients. So if you've used PyTorch, you're familiar with this optimizer.zeroGrad. This works similarly. It essentially initializes the gradient on all of our nodes to 0, which you want to do because if you run the backward pass multiple times, the gradient will keep accumulating and get larger and larger. So zeroGrad will just zero out the gradient. Then we'll run softmax.applyBackward against our loss gradient. So we're passing our loss gradient in to this multiply node, and then we're going to run along this graph the backward pass. And then what we can say is operations softmax grad equals x.grad. So in our backward pass, the network will stick a gradient onto every parameter that needs a gradient. This is very similar to how it works in PyTorch. If we have a parameter node and we set the needs grad equals true flag, the gradient will be accumulated onto that node. So now we can verify stage softmax grad, operation softmax are equivalent. Softmax grad. And they are, which is good. As a bonus, we can actually check out the derivative chains. So I've written a little small utility function that will generate the derivative chains up to a certain point. So we can do this for x. So we can see the chain of derivatives that we have to add and multiply together to get the derivative of loss with respect to x. So these little symbols, the little d, the partial d symbol, and divided by another d symbol equals the derivative of one thing with respect to another. So the derivative of the top thing with respect to the bottom thing. And when I just write the d without anything after it, that means derivative of loss. So what this is saying is the derivative of our loss with respect to our parameters x. Another way of saying how much will our loss change if we change our parameters x equals all of these things added and multiplied together. All right, so we just built a miniature PyTorch. This works very, very similarly to PyTorch. We define these nodes, and the nodes know how to do forward and backward passes on themselves, and we link them together to do a complex operation. Okay, now let's do something a little bit more interesting. Let's do an entire 2-layer neural network. We need a few additional operations to make this work. So we need matrix multiplication, which in the forward pass is just x times w, or x times the weights. We need an add node, so we can add the bias to x times w. And we need ReLU, which is our nonlinear activation function, which basically sets any value below 0 to 0. And we covered all of this in previous lessons. Okay, so we could write our matrix multiplication node. So we just say forward self x w. So w is going to be our weight parameter, and we'll just return x times w. And in the backward pass, we'll take in our gradient. We'll grab x and w out of the cache, and we will return. So this is the derivative with respect to x, grad at w.t, and then x.t at grad. So t is transpose. It's basically turning the matrix. Okay, and then we have our add node. So in the forward pass, we do self xb, and we'll just return x plus b. And then in the backward pass, we will return our gradient and our gradient. That's because any change to an input will change the output the exact same amount. So our gradient is just passed directly into each input parameter. So that's our add node. And the last node we need to implement is our ReLU node. So we will write a little forward pass for ReLU. So we'll return numpy.maximum x0. We're essentially setting anything below 0 to 0. Then in the backward pass, it's a little bit more complicated. So we grab x out of the cache, and we will define a variable called newGrad. All right, and then we'll just say newGrad, x is less than 0 equals 0. So why are we doing this? So in the forward pass, anything that was below 0 in the forward pass, any x value below 0 was set to 0, and therefore did not affect the gradient further along in the network. It didn't affect the output because it was 0. So here all we're saying is if we set a value to 0 in the forward pass, also set the gradient to 0, so that parameter, so we don't accidentally adjust parameters based on that gradient value. Okay, so that is ReLU. All right, and one quick thing before we move on to looking at this neural network, one thing that frameworks like PyTorch do is they fuse operators. So if you're working with a GPU, often you can send your data into the GPU and then do a lot of processing very, very quickly. So computation on a GPU is fast, but memory transfers are very slow. It takes a long time to copy data in and out of the GPU. So it's very common to basically transfer data in once, do a bunch of operations on it, and then copy the data out. That doesn't necessarily work well in a world where we define these individual nodes for single operations. Instead, what we need to do is fuse our operations. And I'll show you a couple of examples of fused operators. This will be very relevant as you try to tune networks for performance and understand things later on. Okay, so in the forward pass of our softmax, we'll just return our softmax function that we defined earlier. It's been a while. So this is the softmax function. So we're just going to call this as our fused forward pass. All right, and then in the backward pass, we just grab x out of our cache. All right, and then we need to recalculate the softmax because we need the actual softmax values for our gradient function. So that's the fused softmax. We can also fuse the entire kind of linear layer in a neural network, a dense layer. So here we'll take self x w b, and then we'll return x at w plus b. And we will also do a backward pass. And here we have 3 values, xwb, self.cache, and then we'll return grad at w, x.t at grad, and grad. I missed the .t here, so we just add that in. All right, so those are our derivatives. That's our derivative for the entire dense layer, and this is how we might conceivably fuse a kernel. This would be called a fused kernel for our dense layer. Okay, so we now have all of the operations we need to define a 2-layer neural network. So let's actually import our data. If you're interested in where the data came from, feel free to look at this dataset wrapper code. I've used this in a couple of, actually just one previous lesson also. So basically we're going to load in telescope observation data of galaxies and quasars, and we're going to try to determine what was in that observation. So this is the same thing we did in our earlier lesson on classification with neural networks. Okay, and then we can just take a quick look at the data. So as you can see, this is the first 2 rows of the data, and there's a bunch of different columns. I won't really go too much into what they are, but they're all different observations from a telescope. Okay, then we need to one-hot encode our data so we can use it for classification. We're doing 3-class classification. So in this case, we're just going to write a little encode function, which will take in our target and the maximum value. So we'll define a matrix with 3 columns. We'll figure out our indices and we'll encode them. This is the same thing we did much earlier in this lesson, where we're just generating a one-hot encoded matrix. And then we'll take a look at our first 5 rows of train Y. So you can see this is 1 in the position of the correct class and a 0 otherwise. Okay, we can now initialize our weights and biases for a 2-layer network. So we'll just do numpy random seed 0. This is just to ensure that if we rerun the cell, we'll get the same weights and biases. Okay, so in the first layer, we will map from our 13 features to 10 new features. Okay, and then we will add in our bias to each row. And in our second layer, we'll map from our 10 features to our 3 targets that we're trying to predict. And then B2 will just be a bias against that. Okay, so now we can define our X and our Y parameter nodes. So X equals parameter, train X, we don't need a gradient against our parameters. We only need a gradient, we don't need a gradient against our inputs. We only need a gradient against our parameters, which is confusing, I know, because this is called a parameter node, but these are the inputs to our network, and our parameters are the weights and biases. All right, and then we will initialize our parameter node for our weights. And then we will initialize our parameters for B1. So this is our first layer weight and bias. Then what we need to do is find a matrix multiplication. So this is just a mat mul node. It's multiplying X by our weights. Then we can add in our bias. Okay, and then the output we will apply ReLU to. So this is the output of our first layer, layer 1. Then we can again get our weights and biases for our second layer. And then we'll again do a matrix multiplication and an add. And we will end with a softmax on the output of the second layer. Okay, this is a more complex graph than before, but we can still generate a graph here. So this is the graph of our 2-layer neural network. We take our inputs X and W, we do a matrix multiply, we add in our bias, we apply ReLU, we do another matrix multiply, we add in a bias again, and then we apply a softmax. Okay, and then we can take a look at our predictions. So we can just apply our softmax forward and take a look at the first 2 rows of our predictions, which gives us this. So this is saying there's a 51% probability that the first row belongs to the first class, 29% probability it belongs to the second class, and so on. Then we can take a look at the graph of the backward pass of our network, which looks like this. We start at our softmax node, our output node, and we pass the gradients back into pass nodes until we get to the beginning. And in these parameter nodes, we store the gradient, so we can actually update the parameter values. All right, so now we can apply the backward pass. We first zero our gradient, then we compute our loss gradient using the NLL grad function from before. We apply our network backwards using apply backward, and we can run that. Okay, then we can take a look at our derivative chains. And what we'll see now is that our parameters have gradients associated with them. So for example, our W2, our weight in our second layer, now has gradients. We can also, against this parameter, look at our partial derivative chain because we ran this derivative chains function. So we can see that the derivative of our loss with respect to W2 is the derivative of our softmax with respect to the output of layer 2 times the derivative with respect to the output of layer 2 times the derivative with respect to the output of layer 1 times W2 times the derivative of the output of layer 1 times W2 with respect to the derivative of W2. So by the chain rule, multiplying all this out gives us the derivative of loss with respect to W2. We are missing one term here, which is the derivative of loss with respect to the softmax of Z2. But in this case, we're just assuming that that is multiplied out. Then we can also do the same thing for our layer 1 weight. It's a little more complicated, so I won't read it all out, but there you go. We've just built a computational graph and used it to do a full forward and backward pass of a network. Okay, and I won't type all this out, but we can actually just write all that code manually for a forward and backward pass and verify that it worked. So we can do numpy.allClose L1 wgrad, which is this manual method of calculation, and we can take a look at w1 param.grad and just verify that they are the same, which they are. So we can see that our computational graph worked and our backward pass worked. Okay, we did a lot in this lesson, and hopefully you learned a lot about how gradients flow through a network and how to break down a derivative into steps. I highly, highly, highly encourage you to play around with defining your own nodes, changing around how the nodes work, and seeing how that changes the gradients and how the gradients flow through this network. This is really important, and it'll help you understand at a very low level how neural networks work and how backpropagation works. All right, in a future lesson, we'll learn how to do this automatically with PyTorch. It is important that you understand how to do it manually, though. All right, hope you enjoyed this lesson. I'll see you for the next one.